Some nights when you look up at the sky, there's a light that doesn't flicker, steady, ancient, impossibly bright. Not a star. Something heavier. Something that's been watching Earth for longer than memory itself. That light is Jupiter. And tonight we're drifting toward the giant that guards us all. Before we begin, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell not for noise, but so the next quiet night can find you again. Now, let's drift. Jupiter hangs in darkness 2,000 times farther than the moon. Yet you can see it with nothing but your eyes. No telescope, no camera. Just you and the oldest light your ancestors also watched. 4.5 billion years ago, when our solar system was nothing but dust and violence, Jupiter was already forming, pulling hydrogen into itself like breath into lungs. It grew so fast, so large, that it became something between a planet and a failed star, the largest world our sun ever made. Scientists suggest Jupiter weighs more than twice all the other planets combined. If you place 318 Earths on a cosmic scale, you'd need every single one just to balance Jupiter's mass. And yet, for all that weight, Jupiter is mostly emptiness. Hydrogen gas, helium, clouds, storms that never die. A giant made of whispers. But size alone doesn't explain what Jupiter really does. It doesn't just exist out there in the cold dark. It shapes everything. The orbits of comets, the survival of Earth, the very possibility of you sitting here now, breathing quietly, while distant storms rage in silence. On January 7th, 1610, a man in Padua named Galileo Galilei pointed a small telescope at Jupiter. He saw what no human had ever seen, 4 tiny lights moving in a line beside the giant world. Not stars, not illusions, moons. 4 worlds orbiting another world that wasn't Earth. In that single moment, the universe became larger, stranger and more beautiful than anyone had imagined. Those moons, Io, Europa, Ganymede, Callisto, still circle Jupiter tonight, just as they did when Galileo first whispered their secret to the cosmos. We know now that Jupiter has 95 moons. Some are worlds of fire, others oceans locked beneath miles of ice. But we'll drift to those later. For now, just imagine a single planet holding an empire of moons, each one a mystery waiting in the cold. Jupiter doesn't only shape moons, it shapes danger itself. Every asteroid that wanders too close, every comet that falls sunward from the edge of darkness, Jupiter feels it. And often, Jupiter catches it. In July of 1994, astronomers watched as a comet called Shoemaker-Levy 9 fell into Jupiter's atmosphere piece by piece, like stones thrown into an ocean that swallows everything. The impacts were so violent, they left scars larger than Earth, dark bruises in Jupiter's clouds that lasted for months. If Jupiter hadn't been there, that comet might have continued inward. It might have struck Earth instead. We would never have known it was coming, and the world you live in now, the cities and forests and quiet nights might never have been. Scientists believe Jupiter has done this thousands of times, millions maybe. Catching bullets meant for us, absorbing them into storms we'll never fully understand. A cosmic guardian that asks for nothing, not even our attention. But how does Jupiter do this? How does something so far away protect something so small? The answer is gravity. Jupiter's mass bends space itself, creating an invisible well so deep that anything passing nearby either falls in or gets flung away into the dark. It doesn't choose to protect Earth. It simply exists. And by existing, it changes the rules of survival for everything closer to the sun. Some researchers even suggest that without Jupiter, Earth might never have formed at all. In the early chaos of our solar system, when planets were still colliding and growing, Jupiter's gravity may have cleared the inner solar system of too much debris. It gave Earth room to breathe, to cool, to gather water from comets without being destroyed by them. We owe our oceans to Jupiter. We owe our atmosphere to Jupiter. We might owe everything to a world we can barely see without help. Think about that for a moment. A planet you've never touched, never visited, never even thought about. Most days has been quietly keeping you alive since before your species existed. Since before mammals walked. Since before the first fish crawled onto land. Jupiter has been there, steady, immense, patient. And yet, Jupiter itself is a place of chaos. A place where winds scream at 400 miles per hour. Where lightning bolts 1,000 times more powerful than Earth's crack. Through clouds of ammonia and methane. Where the sky is not blue but cream and rust and burnt orange. Where there is no ground to stand on, no surface to touch. Only falling forever into heavier and heavier gas until pressure crushes everything into states of matter that exist nowhere else in the known universe. If you could somehow survive the journey, if you could fall through Jupiter's clouds in a ship that wouldn't melt or implode, you would pass through layers of weather that make Earth's hurricanes look like soft breezes. You would sink past storms the size of continents, past clouds made of chemicals that would burn your lungs if you breathed them. And deeper still, past the point where gas becomes liquid, where pressure turns hydrogen into a metal that conducts electricity like copper wire. And deeper. Until even light stops making sense. But no one has ever gone there. No one ever will. Jupiter is a place you can only know from a distance through numbers and images and the quiet hum of machines we send to look for us. And maybe that's how it should be. Some places are meant to remain untouched. Some mysteries are meant to stay mysterious. Still we look. We've been looking for 400 years now, ever since Galileo. And every time we look closer, Jupiter surprises us. It spins faster than any other planet, completing one full rotation in less than 10 hours. That means a day on Jupiter is shorter than a workday on Earth. The entire world turns storms, and all in the time it takes you to sleep and wake. And because it spins so fast, Jupiter bulges at its equator. It's not a perfect sphere. It's slightly squashed like a ball of dough spinning on a potter's wheel. If you measured Jupiter from pole to pole, it would be 9,000 kilometers shorter than if you measured it across the middle. A giant flattened by its own speed. Yet for all its violence, all its speed, all its crushing power, Jupiter has a strange kind of beauty. The bands of color that wrap around it, the swirls and eddies in its atmosphere, the way light plays across clouds that have never known rain. It's a painting that never stops moving, never repeats, never stays still. A living canvas of gas and storm and ancient light. And tonight, under that same light, you're lying here listening. Maybe you're wondering what it would be like to see Jupiter up close, to float beside it in the silence of space, watching storms churn and lightning flash in skies that have no shore. Maybe you're wondering if Jupiter ever wonders about us, if it knows we're here at all. It doesn't. It can't. But it doesn't need to. Jupiter's job was finished long ago when it swept the inner solar system clean and gave Earth a chance to become something soft, something green, something that dreams. And now with that thought settling gently in your mind, we're ready to drift deeper, because Jupiter's protection is only the beginning of its story. There's something else happening on that distant world, something that's been raging for longer than human civilization. A storm so vast, so impossibly enduring, that it makes every storm you've ever known look like a whisper. That storm we're drifting toward now has a name, the Great Red Spot. And it's been spinning for longer than anyone alive today can remember. Longer than their grandparents, longer than nations, longer perhaps than human civilization itself. In 1665, an Italian astronomer named Giovanni Cassini noticed something strange through his telescope, a dark oval mark on Jupiter's face. He sketched it carefully, not knowing he was documenting what might be the oldest storm anyone has ever seen. 360 years later, that storm is still there, still spinning, still refusing to die. Think about that for a moment. Every hurricane you've ever heard of on Earth, every typhoon, every cyclone, they last days. sometimes weeks. The longest-lived tropical cyclone ever recorded on Earth survived for 31 days before it finally exhausted itself. 31 days, and we considered that remarkable. The Great Red Spot has lasted for at least 3.5 centuries, maybe longer, maybe much longer. Scientists suggest the storm might be even older than Cassini's first observation. Some researchers believe it could have been spinning for 500 years. Others think it might be 1,000 years old or more. We simply don't know when it began. We only know it hasn't stopped. Not for wars, not for ice ages, not for the rise and fall of empires. It just keeps turning patient and enormous in a sky that knows no seasons. But here's what makes it even stranger. The Great Red Spot is shrinking. In the 1800s, astronomers measured it at roughly 40,000 kilometers across, wide enough to swallow 4 Earths side by side. By 1920, it had narrowed to about 33,000 kilometers. By 2014, it was 20,000. And in recent observations from NASA's Juno spacecraft, the storm measures only about 16,000 kilometers at its widest point. It's disappearing, slowly, quietly, like a flame burning lower each year, and no one knows why. Some researchers think the storm is running out of energy. Others believe it's being choked by changes in Jupiter's atmosphere, compressed by winds that flow around it like water around a stone. Still others wonder if it's not shrinking at all, but simply changing shape, reorganizing itself into something we don't yet have the eyes to see. The truth is, we're watching something die, and we don't know if death is the right word for what's happening. But even as it shrinks, the Great Red Spot remains one of the most powerful storms in the solar system. Wind speeds at its edge reach 430 kilometers per hour. That's faster than the strongest tornadoes on Earth, faster than the jet stream, faster than anything you've ever felt push against your face. And those winds have been blowing without pause for longer than the United States has existed. What keeps it alive? On-Earth hurricanes need warm ocean water to survive. When they move over land or cold water, they weaken and die. But Jupiter has no surface, no ocean, no land, just gas layered upon gas, sinking deeper into pressure and heat. The Great Red Spot doesn't need an ocean because it is the ocean. It feeds on Jupiter's internal heat, on the energy rising from thousands of kilometers below, where hydrogen behaves in ways that don't make sense to human intuition. NASA's Juno mission, which arrived at Jupiter in July of 2016, has been studying the storm more closely than ever before. Juno flies closer to Jupiter than any spacecraft before it, skimming just 5,000 kilometers above the cloud tops, close enough to feel the pull of Jupiter's radiation, close enough to see details no telescope on Earth could ever resolve. And what Juno discovered changed everything scientists thought they knew about the Great Red Spot. The storm isn't shallow. It's not just a swirl in the upper atmosphere. Juno's instruments revealed that the Great Red Spot reaches down at least 350 kilometers into Jupiter's atmosphere. That's deeper than the distance from New York to Washington, D.C., deeper than the height of Earth's mesosphere, a column of spinning gas taller than 100 Mount Everests, all rotating as one vast engine of wind and chaos. But it gets stranger still. The storm is cold at the top and warm below. Scientists measured temperatures in the storm's upper clouds at about negative 160 degrees Celsius. Cold enough to freeze carbon dioxide solid. Cold enough to shatter steel. Yet deeper in, where Juno's radio instruments can still sense the storm's movement temperatures rise to nearly 0 degrees Celsius, warm by Jupiter's standards, almost comfortable if you could somehow stand there without being crushed or poisoned or torn apart by wind. And the colors, those swirling reds and browns and creams that make the Great Red Spot so hypnotic to watch. For a long time, scientists weren't sure what caused them. They knew the colors came from chemicals in Jupiter's atmosphere, but which chemicals and why red? Why not blue or green or yellow? Research now suggests the red color comes from complex organic molecules created when sunlight breaks apart. Simpler chemicals like ammonia and methane. These molecules, called chromophores, absorb blue light and reflect red, giving the storm its signature rust-colored hue. It's the same chemistry that turns autumn leaves red and brown, the same process that makes blood the color it is. Life and death painted in the same shades across 40 million miles of emptiness. But the Great Red Spot isn't alone. Jupiter's atmosphere is crowded with storms. Dozens of them. Hundreds maybe. Some are white, others brown. Some last years, others only months. In the year 2003, smaller white storms merged together to form a new storm now called Oval BA. Astronomers nicknamed it Red Spot Jr. because it also turned red, though no one is entirely sure why. For a while, scientists thought Oval BA might grow to rival the Great Red Spot, but it hasn't. It remains smaller, younger, less enduring. And then there are the storms we can't even see from Earth. Storms that exist in Jupiter's polar regions, invisible to telescopes pointing from the side, but captured by Juno's cameras as it flies overhead. Cyclones, some of them larger than Earth, arranged in perfect geometric patterns around Jupiter's north and south poles. 8 storms circling the North Pole, 5 circling the south, all spinning, all stable, all locked in a dance that never stops. Why do they arrange themselves this way? Why don't they merge or drift apart? Scientists are still trying to understand. It's as if Jupiter's atmosphere has rules we haven't learned yet, patterns we can observe but not explain, beauty we can see but not predict. You might wonder if storms on Earth are caused by temperature differences between warm and cold air. What causes storms on Jupiter? The answer is similar but stranger. Jupiter generates its own heat. Unlike Earth, which is warmed almost entirely by the sun, Jupiter radiates more energy than it receives. It's still glowing faintly from the heat of its own formation. And that heat rising from below creates instabilities regions where warm gas pushes upward and cold gas sinks down, stirring the atmosphere into motion. Add to that Jupiter's rapid rotation. A 10-hour day means the entire planet is constantly spinning, dragging its atmosphere along with it. This creates zones and belts, alternating bands of clouds that flow in opposite directions. Where these bands meet, turbulence forms. Eddies and swirls and storms that feed on the friction between them. The Great Red Spot sits at one of these boundaries, a massive vortex trapped between 2 rivers of wind, flowing past each other at different speeds. And unlike hurricanes on Earth, which spin counterclockwise in the northern hemisphere and clockwise in the southern, the Great Red Spot spins counterclockwise even though it's in Jupiter's southern hemisphere. It's what scientists call an anticyclone. A high-pressure system, the opposite of what we expect. And that difference might be part of why it's lasted so long. High-pressure systems tend to be more stable, less likely to fall apart when disturbed. But even knowing all this, we still can't fully explain why the Great Red Spot has survived for centuries, while other storms come and go. We can't predict when it will finally disappear, or if it will disappear at all. Maybe it will shrink into nothing. Maybe it will stabilize at a smaller size and spin for another 1,000 years. Or maybe one day we'll look up and it will simply be gone, leaving behind only a memory and a gap in Jupiter's clouds where something immense once lived. There's a strange kind of sadness in that thought. A storm older than memory, older than most of human history, quietly fading in a place no one will ever visit. No one will stand on Jupiter's surface and watch the last rotation of the Great Red Spot because there is no surface to stand on. No one will feel the final gust of wind or hear the last rumble of its endless thunder. It will simply stop, and the universe will continue indifferent. But for now, tonight the Great Red Spot still spins, still storms, still paints its rusty swirl across a world too large to hold. And if you ever find yourself looking up at Jupiter, that bright, steady light in the night sky, remember that you're looking at a place where storms never sleep, where winds never rest, where chaos has learned to endure. And speaking of things that endure, there's something else around Jupiter that never stops. Something invisible, something powerful enough to reach across millions of kilometers and touch everything nearby. An invisible shield that protects Jupiter's moons and punishes anything that comes too close. That invisible shield is a magnetic field, and it's stronger than anything else in the solar system except the sun itself. Strong enough to trap particles, strong enough to bend radiation, strong enough to kill. In December of 1973, a spacecraft called Pioneer 10 became the first human-made object to fly past Jupiter. Engineers on Earth held their breath as the probe approached, uncertain if it would survive. They knew Jupiter had a magnetic field. They just didn't know how powerful it really was. Pioneer 10 plunged through invisible zones of radiation so intense that its instruments began to fail. Circuit boards sparked, sensors flickered. For a moment, mission controllers thought they might lose the spacecraft entirely, but Pioneer 10 survived, barely. And when its data finally reached Earth, scientists realized they had underestimated Jupiter by an astonishing margin. Jupiter's magnetic field wasn't just strong, it was 20,000 times stronger than Earth's. A force so immense it wrapped around the planet like an invisible ocean stretching millions of kilometers into space. We call this region the magnetosphere. And Jupiter's magnetosphere is the largest single structure in the solar system. If you could see it, if magnetic fields glowed like clouds or oceans, Jupiter's magnetosphere would appear larger than the full moon in Earth's sky. Larger than the sun itself, from our perspective. A bubble of invisible force so vast, it takes light several seconds to cross from one side to the other. The magnetosphere begins where Jupiter's magnetic field meets the solar wind, that constant stream of charged particles flowing outward from the sun. Normally, the solar wind would strip away a planet's atmosphere particle by particle over millions of years. But Jupiter's magnetosphere pushes back. It creates a boundary, a wall in space where the solar wind crashes and flows around Jupiter like water around a stone. Scientists call this boundary the magnetopause. And depending on the strength of the solar wind, the magnetopause can shift inward or balloon outward, sometimes reaching as far as 600 million kilometers from Jupiter, far enough to touch Saturn's orbit. But the magnetosphere isn't just a shield, it's also a trap. Any charged particle that wanders too close gets caught spiraling along invisible magnetic field lines, accelerating faster and faster until it reaches speeds close to the speed of light. These particles, mostly electrons and protons, form radiation belts around Jupiter. Belts so intense they would kill an unprotected human in minutes, maybe seconds. Earth has radiation belts too. We call them the Van Allen belts, discovered in 1958 by physicist James Van Allen. They're dangerous, yes. Satellites passing through them need extra shielding. Astronauts avoid them when possible. But Jupiter's radiation belts make Earth's look gentle, harmless almost. The radiation near Jupiter is 1,000 times more intense than anything around Earth, 1,000,000 times more intense in some regions. It's not a place meant for life. It's not a place meant for anything soft or fragile or alive. And yet, spacecraft keep going there. After Pioneer 10 came Pioneer 11, then Voyager 1 and Voyager 2 in the late 1970s. Then Galileo, which orbited Jupiter for 8 years, starting in 1995. Then Cassini flying past, on its way to Saturn. Then New Horizons, briefly in 2007. And now, Juno's still circling Jupiter, still gathering data, still enduring radiation that slowly, inevitably damages its electronics. Engineers designing these missions knew the radiation would be a problem, so they built the spacecraft with extra shielding, layers of aluminum and titanium, hardened electronics, redundant systems. And even then, they knew the spacecraft wouldn't last forever. Juno's mission was originally planned for 2 years. It's now in its 9th year, far exceeding expectations, but every orbit brings it closer to failure. Every pass through Jupiter's radiation belts chips away at its circuits bit by bit, until one day it will simply stop responding. But why is Jupiter's magnetic field so strong? The answer lies deep inside the planet in a region no human will ever see. Scientists believe that far below Jupiter's clouds, where pressure becomes so extreme that hydrogen stops behaving like a gas and starts behaving like a liquid metal, electric currents flow in vast loops. These currents generate the magnetic field the same way currents in a wire create magnetism. But unlike a wire, Jupiter's metallic hydrogen ocean is thousands of kilometers deep, spinning with the planet's 10-hour rotation, generating a magnetic dynamo more powerful than anything we could ever build. And that magnetic field doesn't just extend outward. It reaches inward too, touching Jupiter's moons, wrapping around them, interacting with them in ways both beautiful and violent. Io, the innermost of the 4 large moons, orbits directly through one of Jupiter's most intense radiation belts. It's bombarded constantly by high-energy particles. Its surface is scorched. Its volcanoes, more than 400 of them, erupt continuously, spewing sulfur and gas into space. Some of that material gets caught by Jupiter's magnetic field, forming a glowing ring of plasma called the Io-plasma torus. The Io-plasma torus is one of the strangest structures in the solar system, a donut-shaped cloud of ionized gas, mostly sulfur and oxygen, circling Jupiter at the same distance as Io's orbit. It glows faintly in ultraviolet light, invisible to human eyes, but bright to instruments designed to see it. And it's hot. Not hot like fire, but hot in the way plasma is hot. Millions of degrees, though. The gas is so thin it would feel cold if you could somehow touch it. Particles from the Io-plasma torus spiral along Jupiter's magnetic field lines, funneling down toward Jupiter's poles. And when they strike the upper atmosphere, they create auroras. Not the soft green curtains of Earth's northern lights, but auroras 100 times brighter, 1,000 times larger. Auroras that dwarf entire continents. Auroras that never stop. Scientists using the Hubble Space Telescope and ground-based observatories have been watching Jupiter's auroras for decades. They flicker and pulse, sometimes brightening, when the solar wind strengthens, sometimes dimming when it weakens. But they never disappear. Not completely. Because Jupiter's auroras aren't powered by the sun alone. They're powered by Io, by the constant flow of material from Io's volcanoes into Jupiter's magnetosphere. As long as Io keeps erupting, as long as Jupiter's magnetic field keeps spinning, the auroras will continue to glow. And the sound. Jupiter's magnetosphere makes sounds. Not sounds you could hear with your ears, because sound can't travel through the vacuum of space, but radio waves. Electromagnetic waves that oscillate at frequencies we can detect and convert into audio. In the 1950s, radio astronomers on Earth began picking up strange bursts of radio noise from Jupiter. They called them decametric emissions. Short, sharp bursts that sounded like static or clicks when played through a speaker. At first, scientists thought the signals might be coming from lightning in Jupiter's atmosphere. But the pattern was wrong. The signals were too regular, too structured. Eventually, researchers realized the radio waves were being generated by electrons, spiraling along Jupiter's magnetic field lines. As these electrons spiral, they emit radiation, including radio waves. And when those waves reach Earth, we can listen to them. Jupiter is broadcasting constantly a symphony of electromagnetic noise that we're only just beginning to understand. There are other sounds too. Whistlers, chorus waves, low-frequency hums that rise and fall like music. None of it is intentional, none of it carries meaning. But it's there a side effect of Jupiter's magnetic field interacting with the charged particles around it. If you could float in space near Jupiter, surrounded by the right instruments, you could listen to the planet sing, but you wouldn't want to stay long, because the radiation would be killing you. Slowly at first, then faster. Your cells would begin to break down. Your DNA would fragment. Even inside a spacecraft, even with shielding, the dose would accumulate. There's a reason no crewed mission to Jupiter has ever been seriously planned. The radiation makes it nearly impossible. We can send robots. We can send cameras and sensors and instruments that don't care about dying. But we can't send people. Not yet. Maybe not ever. Europa, Jupiter's fourth largest moon, orbits farther out than Io, but it's still deep inside the magnetosphere, still bathed in radiation. And yet, beneath its icy surface, scientists believe there's an ocean, a real ocean. Liquid water, perhaps warmed by tidal heating, perhaps holding life. But reaching that ocean would require drilling through kilometers of ice while enduring radiation that would fry any known electronics in hours. It's one of the great challenges of space exploration. How do you explore a place that actively destroys everything you send? Their NASA's upcoming Europa Clipper mission, set to arrive at Jupiter in the 2030s, won't orbit Europa. It can't. The radiation would kill the spacecraft too quickly. Instead, it will orbit Jupiter itself, swooping past Europa every few weeks, gathering data during brief flybys before retreating to safer distances. Even then, the spacecraft will accumulate massive doses of radiation. Engineers estimate it will survive for only a few years before its systems fail. But maybe that's enough. Maybe a few years of data, a few dozen close passes will be enough to answer the question scientists have been asking for decades. Is there life in Europa's ocean, life that evolved in darkness beneath ice, shielded from the universe by Jupiter's radiation, but also paradoxically powered by it? Because the radiation that makes Europa so hostile might also be what keeps its ocean liquid. The same magnetic field that kills might also create. There's a strange symmetry in that. A shield that protects and destroys. A field that traps and creates. A boundary between safety and death that shifts with the solar wind, never quite stable, never quite predictable. Jupiter's magnetosphere is many things, but most of all, it's a reminder that the universe doesn't care about our categories. Things can be both shelter and storm, both cradle and grave. And as we drift away from this invisible ocean, as we let the magnetosphere fade behind us, another mystery waits. Because Jupiter isn't just wrapped in magnetic fields and radiation. It's wrapped in something even stranger. Something that challenges every assumption we have about what a planet should be. That mystery is simple and strange. Jupiter has no ground, no surface, no place you could ever stand no matter how advanced your technology became. If you fell toward Jupiter, you would fall forever through layers of gas that grow denser and hotter until pressure crushed you into atoms, until you became part of Jupiter itself. Most people, when they imagine a planet, imagine something solid, rock, metal, ground beneath feet. We think of Mars red and dusty. We think of Earth green and blue. We even think of Mercury and Venus hellish, but at least possessing something you could technically touch. But Jupiter defies that imagination. Jupiter is mostly emptiness held together by its own weight. A ghost of hydrogen pretending to be solid. The question scientists have asked for decades is, where does Jupiter's atmosphere end and its interior begin? And the answer, uncomfortable and fascinating, is that it doesn't. There's no boundary, no moment where gas becomes something else. Just a gradual transition, pressure building, slowly temperature rising degree by degree until the very definition of gas stops making sense. At the top, in the regions we can see through telescopes, Jupiter's atmosphere is almost familiar. Clouds made of ammonia, ice floating in hydrogen and helium. The temperature here is cold, -140 degrees Celsius. Cold enough to freeze nitrogen, cold enough that if you somehow survived the lack of oxygen and the radiation, you'd still freeze solid in seconds. But descend deeper just a few dozen kilometers and the temperature rises. The pressure builds. You pass through the ammonia clouds into a layer scientists believe contains water. Not liquid water, not yet, but water vapor mixed with other compounds. Hydrogen sulfide, perhaps, methane, chemicals that on Earth would smell terrible, but here exist in concentrations and pressures that make smell irrelevant. There's no one to smell them. No nose that could survive long enough to register the scent. Deeper still, perhaps 100 kilometers down, pressure reaches 1 bar, the same pressure as Earth's atmosphere at sea level. This is the level scientists use as a reference point when talking about Jupiter's surface. Even though there's nothing surface-like about it, it's just a marker, a place where pressure equals something we understand. But keep falling, and pressure keeps building. 2 bars, 10 bars, 100 bars. Each bar represents the weight of Earth's entire atmosphere pressing down on every square centimeter. And Jupiter has thousands of bars, millions eventually near the core. At 1,000 bars, roughly 3,000 kilometers deep, something extraordinary happens. The hydrogen around you, still technically a gas, starts to behave like a liquid. Not because it cools down, the opposite. Temperature at this depth reaches several thousand degrees Celsius, hot enough to melt rock, hot enough to glow if there was anyone to see it glow. But the pressure is so immense that hydrogen molecules are forced closer together than they want to be. They can't escape each other. They flow like oil, thick and strange in a state of matter that doesn't exist naturally anywhere on Earth. Scientists call this liquid molecular hydrogen, and it makes up a huge portion of Jupiter's interior, a shell thousands of kilometers thick, surrounding something even stranger below. But before we descend, consider what you'd experience at this depth. The pressure would be crushing you with the weight of 1,000 Earth atmospheres. The temperature would vaporize any known material, and yet the hydrogen around you would be flowing, moving, convecting. Warm hydrogen rising, cool hydrogen sinking, creating currents vast enough to power Jupiter's weather systems above. And you'd still be falling, deeper, always deeper, until you reach a pressure of about 2 million bars, a number so large it's hard to make meaningful. 2 million times the pressure at Earth's surface. And here, around 4,000 kilometers down, hydrogen undergoes another transformation. It becomes metallic. Metallic hydrogen, a substance predicted by physicists in 1935, but never created in a laboratory for more than a fraction of a second. Under enough pressure, hydrogen's electrons are squeezed away from their atoms. They become free-flowing like electrons in copper wire. The hydrogen itself becomes shiny, reflective, electrically conductive, a metal made from the lightest element in the universe. This metallic hydrogen ocean is where Jupiter's magnetic field is born. Electric currents flow through it, driven by Jupiter's rotation. These currents create the magnetosphere we talked about earlier, the invisible shield, the radiation belts. All of it originates here in a place no spacecraft could ever reach, no instrument could ever sample. We know it exists only because of its effects, because of what it does to the space around Jupiter. But we've never seen it, never touched it, never measured it directly, and still you'd be falling. The metallic hydrogen layer extends for tens of thousands of kilometers, maybe more. Scientists aren't sure exactly how thick it is because we can't see inside Jupiter. We can only make educated guesses based on Jupiter's mass, its gravitational field, the way it wobbles slightly as its moons tug on it. All of these measurements tell us something about what's inside, but they don't give us a perfect picture. It's like trying to understand the inside of an egg by weighing it and shaking it gently. You can guess, you can estimate, but you can't know for certain. Eventually, if you kept falling, you'd reach Jupiter's core, or what scientists think is a core. For a long time, researchers assumed Jupiter had a solid core made of rock and ice, heavy elements that sank to the center during the planet's formation. They estimated this core might weigh 10 to 15 Earth masses, a small planet hidden inside a giant one. But in 2017, data from NASA's Juno spacecraft surprised everyone. Juno's precise measurements of Jupiter's gravitational field suggested the core isn't solid at all. It's diffuse, fuzzy. spread out over a larger region than expected. Some scientists now believe Jupiter's core is partially dissolved, mixed with the metallic hydrogen around it. Others think there might be multiple cores remnants of smaller planets that Jupiter swallowed billions of years ago, still slowly sinking, still merging, still becoming part of Jupiter's deep interior. The temperature at the core, wherever and whatever it is, reaches about 24,000 degrees Celsius, hotter than the surface of the sun, hot enough to make iron boil, hot enough to break molecules into individual atoms. And the pressure. The pressure at Jupiter's core is estimated at 45 million bars, 45 million times Earth's surface pressure, a force so extreme that matter itself behaves in ways we don't fully understand. And yet, despite all the heat, despite all the pressure, Jupiter's core is dark. No light reaches it. No light escapes it. It exists in a kind of crushing, burning, eternal midnight. A place where physics becomes strange and familiar, rules bend until they're barely recognizable. You might wonder if Jupiter is so hot inside, why doesn't it glow like a star? Why didn't it become a star? The answer is mass. Jupiter would need to be about 75 times more massive to generate enough pressure and heat at its core to start fusing hydrogen into helium. That's the process that powers stars. That's what makes the sun shine. Jupiter came close in cosmic terms. It's the largest planet our solar system could produce. But close isn't enough. Jupiter will never ignite. It will never burn. It will only glow faintly with the heat of its own slow contraction, cooling over billions of years, until eventually unimaginably far in the future it becomes cold and dark and still. But that's a future too distant to worry about. For now, Jupiter remains warm. Alive, in a sense, still radiating more energy than it receives from the sun, still glowing in infrared, still convecting, still spinning, still holding itself together through nothing but its own gravity. On Earth, scientists have tried to recreate the conditions inside Jupiter, not out of curiosity alone, but because understanding metallic hydrogen could revolutionize technology. If we could create and stabilize metallic hydrogen at lower pressures, it might be the most efficient rocket fuel ever discovered. It might enable superconductors that work at room temperature. It might change everything. But so far, every attempt has failed. Researchers have compressed hydrogen between diamond anvils, squeezing it with forces that would shatter steel. For brief moments, milliseconds, sometimes they've seen hints of metallic hydrogen. Fleeting glimpses, but it never lasts. The pressure required is simply too extreme. The instant the force is released, metallic hydrogen reverts to ordinary hydrogen gas. It exists only under conditions that, for now, exist naturally nowhere in the known universe except inside giant planets like Jupiter. And maybe that's fitting. Maybe some things are meant to remain beyond reach. Some mysteries are meant to stay mysterious, not out of cruelty, but because the universe is larger and stranger than our capacity to hold it. Jupiter's interior is one of those mysteries, a place we can imagine but never visit, a place we can model but never confirm, a place that exists in equations and simulations but remains fundamentally unknown. Still, we try to understand. We send spacecraft. We build computer models. We compress hydrogen in laboratories and measure how it behaves. We do this because understanding Jupiter means understanding how planets form, how solar systems evolve, how worlds like Earth came to be possible in the first place. Jupiter is, in many ways, a fossil, a record of what the early solar system looked like. While Earth and the other rocky planets lost most of their original hydrogen and helium, Jupiter kept it, locked it away in its immense gravity well. Jupiter's composition today is roughly the same as it was 4.5 billion years ago. 90% hydrogen, 10% helium, traces of heavier elements. The same mix that made the sun, the same mix that filled the nebula from which everything emerged. By studying Jupiter, we're studying our origins. We're looking back at the chemistry that made us possible, and we're learning that planets can be more than solid spheres of rock and metal. They can be fluid, they can be layered, they can be places where matter exists in states we never encounter on Earth. Places where the rules shift, where pressure rewrites physics, where the familiar becomes alien. And as we drift upward now, leaving the crushing depths behind, we're about to discover that Jupiter has another voice, another way of speaking to the universe. Not through storms or magnetic fields or hidden oceans of metal, but through something even stranger. Something you can almost hear if you know how to listen. That sound is radio waves. Jupiter sings. Not in frequencies you can hear with human ears, but in electromagnetic wavelengths that travel across millions of kilometers of emptiness, carrying messages no one sent. Voices from a world that has no voice. In the spring of 1955, two radio astronomers named Bernard Burke and Kenneth Franklin were studying cosmic radio sources at the Carnegie Institution in Washington, D.C. They pointed their antenna toward the constellation Taurus, searching for faint signals from distant galaxies. But something kept interfering, a burst of static, sharp, irregular, impossible to ignore. At first, they thought their equipment was broken. Then they thought it might be terrestrial interference, radio stations, cars, electrical storms. But the interference came at the same time every night. Same direction, same pattern. And slowly and possibly they realized what they were hearing. Jupiter, broadcasting radio waves strong enough to detect from Earth with equipment designed for deep space observation. A planet closer than any star, louder than most galaxies, filling their instruments with noise. It was the first time anyone had detected radio emissions from another planet. The first time anyone realized that worlds could speak in frequencies invisible to human senses. And Jupiter, it turned out, was one of the loudest voices in the solar system. Scientists now know that Jupiter emits three main types of radio waves: decametric radiation, with wavelengths of tens of meters, decimetric radiation with wavelengths of tens of centimeters, and kilometric radiation with wavelengths of kilometers. Each type is generated differently. Each tells a different story about what's happening in Jupiter's magnetosphere. Decametric radiation comes in bursts, short, intense pulses that sound like clicks or pops when converted to audio. These bursts are connected to Io, Jupiter's volcanically active moon. As Io orbits through Jupiter's magnetic field, it acts like a generator, creating electrical currents that flow along invisible field lines connecting Io to Jupiter. When these currents reach Jupiter's upper atmosphere, they accelerate electrons, which then emit radio waves. The stronger Io's volcanic activity, the stronger the radio bursts. It's as if Io is playing Jupiter like an instrument, plucking magnetic strings that ring across space. But Io isn't the only conductor in this cosmic orchestra. Jupiter itself generates radio emissions independently of its moons. Decimetric radiation, for example, comes from electrons trapped in Jupiter's radiation belts. These electrons spiral around magnetic field lines at speeds approaching the speed of light. As they spiral, they emit synchrotron radiation, a type of electromagnetic energy that includes radio waves. It's the same process that happens in particle accelerators on Earth, but on a planetary scale. Natural, constant, uncontrolled. And then there's kilometric radiation. This type is emitted from Jupiter's polar regions, where magnetic field lines converge and funnel charged particles down into the atmosphere. The radiation is so strong it can sometimes be detected by spacecraft billions of kilometers away. Voyager 1, now far beyond the orbit of Pluto, still occasionally picks up faint echoes of Jupiter's radio voice, a reminder of where it came from, a whisper from a world it left decades ago. When scientists first converted Jupiter's radio emissions into audio, they expected noise, static, randomness. But what they heard was stranger, more structured. Some of Jupiter's radio waves sound almost musical. Rising tones, falling tones, patterns that repeat and vary. They're called chorus waves, though no one composes them. They're the result of electromagnetic interactions, particles bouncing between magnetic field lines, creating feedback loops that resonate like plucked strings or struck bells. Other emissions sound like whistles, sharp descending tones that sweep from high frequencies to low in less than a second. These whistlers are created when lightning in Jupiter's atmosphere sends electromagnetic pulses upward. The pulses travel along magnetic field lines, and because different frequencies travel at different speeds through plasma, they arrive at different times. High frequencies first, low frequencies last. The result is a sound that seems to fall like something dropping through an invisible medium. Jupiter has lightning. Lots of it. Voyager detected it, first capturing brief flashes in Jupiter's night-side clouds. Later missions confirmed it. Jupiter's lightning is similar to Earth's, but more powerful. Individual bolts can be 3 times brighter than the strongest lightning on Earth. And because Jupiter's atmosphere is so thick, so turbulent, lightning occurs constantly, thousands of strikes per hour across the entire planet, each one generating electromagnetic pulses, each one contributing to Jupiter's radio symphony. But here's what makes it even more fascinating. Jupiter's radio emissions aren't constant, they vary. Sometimes Jupiter is loud, broadcasting strongly across multiple wavelengths. Other times, it's quieter, almost silent. The variations depend on many factors: the solar wind's strength, Io's volcanic activity, Jupiter's rotation, even the alignment of Jupiter's magnetic field, which is tilted about 10 degrees from its rotation axis, causing the field to wobble as Jupiter spins. And there's another layer to this, another structure in Jupiter's magnetosphere that contributes to its radio voice. The Io plasma torus, that glowing ring of ionized gas we mentioned earlier. It doesn't just glow in ultraviolet light, it also emits radio waves, low-frequency hums, oscillations caused by waves rippling through the plasma, driven by magnetic field fluctuations, and the constant flow of material from Io. The plasma torus rotates with Jupiter locked to the planet's magnetic field. But it's not a simple ring. It has structure, density variations, hot spots and cold spots, regions where plasma is concentrated, and regions where it's thin. These variations create their own radio signatures, patterns within patterns, harmonies within noise. Scientists studying these emissions have learned to read them like language. Not a language with grammar or meaning, but a language of states. When Jupiter's radio output spikes, it might mean Io is erupting more vigorously than usual. When certain frequencies dominate, it might indicate changes in the solar wind. When whistlers become more frequent, it might suggest increased lightning activity. The radio emissions are data, information about processes happening in regions no spacecraft can visit, translated into electromagnetic waves we can detect from afar. And there's beauty in that translation, in the idea that a planet's invisible violence can become something we can hear. That magnetic fields and trapped particles and volcanic gases can be converted into tones and rhythms and pulses. It's not music in any intentional sense. Jupiter doesn't compose, Jupiter doesn't perform, but the universe left to itself creates patterns, structures, sounds that, when played through speakers, sound almost like they mean something. Radio astronomers on Earth still listen to Jupiter regularly. Amateurs with backyard antennas can pick up some of Jupiter's stronger bursts. During periods of high activity, when Io is particularly active, or when a strong solar storm hits Jupiter's magnetosphere, the emissions become loud enough to detect with relatively simple equipment. People record them, share them online, convert them to audio, and post them on websites. Jupiter's voice broadcasted to anyone willing to listen, but most of Jupiter's radio emissions remain unheard, not because we can't detect them, but because there's so much data, so many frequencies, so many variations that no one has time to listen to it all. Computers analyze most of it. Algorithms search for patterns. Machine learning models try to predict when bursts will occur. But The raw sound, the actual audio of Jupiter's electromagnetic symphony, goes largely unnoticed. Maybe that's appropriate. Maybe some sounds aren't meant to be heard, but only to exist. Maybe Jupiter's radio waves are less a message and more a consequence, a side effect of being large and magnetic and surrounded by moons that bleed gas into space. Still, there's something humbling about the fact that Jupiter has been broadcasting since long before humans existed, long before radios, long before electricity. Jupiter was making these sounds when dinosaurs walked Earth, when the first fish evolved, when life was nothing but single cells floating in ancient oceans. And Jupiter will still be making these sounds long after humanity is gone, long after Earth itself is gone. The radio waves will continue traveling outward at the speed of light, carrying no meaning, no message, just the electromagnetic echo of a giant planet spinning in darkness. And if you ever feel alone, remember this. The universe is full of sounds, not silence, but noise. Radio waves from planets and stars and galaxies. Frequencies we can't hear but can detect. Jupiter alone produces enough electromagnetic energy every second to power every city on Earth. Not that we could ever harness it, not that Jupiter would notice if we tried, but it's there, constant, reliable. A reminder that even in the vacuum of space, even in the cold and empty dark, there are voices, there are songs. Maybe that's why scientists keep listening. Not because they expect to find meaning, but because listening itself is meaningful. Because paying attention to something vast and indifferent reminds us that we're part of a universe that doesn't need us, but includes us anyway. A universe where planets sing and humans for a brief moment in cosmic time have learned to hear. But Jupiter's strangeness doesn't end with sound. There's another mystery deeper and more fundamental. A question about energy itself, about where Jupiter's warmth comes from, and why after billions of years the planet is still glowing. That glow is heat, more heat than Jupiter should have. In 1966, scientists pointed infrared telescopes at Jupiter and measured something impossible. Jupiter was emitting 1.6 times more energy than it received from the sun, more energy out than in. A planet that by all reasonable physics should be cold and dark was instead warm and glowing. At first, some researchers thought their instruments were wrong, telescopes miscalibrated, calculations in error, because planets aren't supposed to generate their own heat. Not rocky planets, not gas giants, not anything except stars which fuse hydrogen in their cores and shine with nuclear fire. Jupiter doesn't fuse hydrogen. Jupiter will never fuse hydrogen. So, where was the extra energy coming from? The mystery deepened when scientists measured other giant planets. Saturn also emitted more energy than it received. Nearly twice as much, in fact. Neptune, incredibly distant and cold, radiated 2.6 times more energy than the faint sunlight reaching it could account for. Even Uranus, the strangest of the ice giants, showed a slight excess, though much smaller than the others. But Jupiter's excess was consistent, measurable, undeniable. Every infrared observation confirmed it. Jupiter glows in wavelengths invisible to human eyes, radiating heat into the cold dark of space, warming itself from within. And the question became not whether Jupiter generates heat, but how. The leading theory proposed in the 1970s is called the Kelvin-Helmholtz mechanism. It's named after Lord Kelvin and Hermann von Helmholtz, two 19th century physicists who studied how gravitational contraction could produce heat. The idea is simple, almost elegant. Jupiter is still shrinking, not quickly, not noticeably, but slowly over millions of years, Jupiter's own gravity pulls it inward, compressing it, and that compression generates heat. Scientists estimate Jupiter shrinks by about 2 centimeters per year. 2 centimeters, less than the width of your thumb. But Jupiter is enormous. Its volume is so vast that even a 2-centimeter reduction in radius releases staggering amounts of gravitational potential energy. Energy that becomes heat. energy that radiates outward through Jupiter's atmosphere and into space. It's the same process that kept Earth's interior molten in its early history. The same process that powers some of the heat in Saturn and Neptune. Gravity pulling inward, matter resisting, and in that resistance friction, heat. Light in frequencies we can measure but not see. But Kelvin-Helmholtz contraction alone doesn't fully explain Jupiter's energy output. Scientists ran calculations, modeled Jupiter's structure, simulated billions of years of slow collapse, and the numbers didn't quite match. Jupiter should be radiating less heat than it is if contraction were the only source. Something else had to be happening, something deeper, something stranger. In the 1990s, researchers proposed a second mechanism, helium rain. It sounds almost poetic, and in a way it is. The theory suggests that deep inside Jupiter in the metallic hydrogen ocean we talked about earlier, helium is slowly separating from hydrogen. Droplets of liquid helium denser than the surrounding hydrogen sink downward like rain through an invisible atmosphere. And as they sink, they release gravitational energy, heat. This isn't rain like we know it. There are no clouds, no thunder, no droplets you could see or touch. Just helium atoms gradually pulling away from hydrogen, falling through a medium that's both liquid and metal, generating warmth as they descend. The process is slow, imperceptible, but over billions of years it adds up, enough to account for the extra energy Jupiter radiates. Scientists believe this helium rain has been falling inside Jupiter for billions of years, perhaps since shortly after the planet formed. And it will continue for billions more until Jupiter's interior cools enough that helium and hydrogen mix evenly again. But that won't happen soon. Not in any timescale humans can comprehend. Jupiter will still be raining helium when the sun swells into a red giant, when Earth is consumed, when everything familiar is gone. But here's where it gets even more interesting. If helium is sinking, then Jupiter's atmosphere should be slowly losing helium. The helium to hydrogen ratio should be changing, dropping over time as helium migrates inward, and measurements from spacecraft have confirmed this. Jupiter's atmosphere contains less helium than scientists expected, less than the primordial ratio present when the solar system formed. The helium isn't missing. It's just deeper than we can see. Locked away in Jupiter's interior, still falling, still heating the planet from within. Saturn shows the same pattern, lower helium abundance in the atmosphere, higher heat output than solar radiation alone can explain. The same helium rain falling through a slightly different interior structure. But Saturn's energy excess is even greater than Jupiter's relative to its size. Scientists think this might be because Saturn is smaller, cooler, and its helium separation happened more recently, releasing more energy in a shorter time. Neptune and Uranus are different. They're ice giants, not gas giants. Their interiors contain more water, methane, and ammonia mixed with hydrogen and helium. But they still generate excess heat, though the mechanism might not be the same. Neptune especially radiates far more energy than it should. Some researchers think Neptune might have additional heat sources, leftover warmth from a massive collision early in its history, or ongoing chemical reactions in its mantle releasing energy through exotic chemistry we don't yet understand. Uranus strangely barely radiates any excess heat. It's almost in thermal equilibrium with the sun's energy. Scientists aren't sure why. Maybe Uranus lost its internal heat during the same catastrophic impact that tipped it on its side. Maybe its interior structure is different enough that helium rain doesn't occur, or occurs much more slowly. Uranus remains in many ways the most mysterious of the giant planets. But back to Jupiter. The temperature at Jupiter's core, heated by both contraction and helium rain, reaches approximately 24,000 degrees Celsius. For context, the surface of the sun is about 5,500 degrees Celsius. Jupiter's core is more than 4 times hotter, not hot enough to fuse hydrogen, but hot enough to disintegrate molecules, hot enough to ionize atoms. hot enough that matter exists in states we can barely imagine. And that heat generated so deep, it will never see light flows upward, slowly, through thousands of kilometers of metallic hydrogen, through the liquid molecular hydrogen layer above it, through the gaseous atmosphere. Convection carries it. Warm material rises, cools, sinks, warms again. The same process that creates weather on Earth, but on a scale that dwarfs anything terrestrial. Convection cells hundreds of kilometers wide, currents that flow for centuries without stopping. This rising heat is part of what drives Jupiter's storms, part of what keeps the great red spot alive, part of what powers the winds, the lightning, the chaos we see in Jupiter's clouds. Without internal heat, Jupiter's atmosphere would be calmer, colder, less dynamic. It might look more like Uranus, whose faint atmospheric features and muted colors suggest a quieter, less energetic interior. Scientists can measure Jupiter's heat output with remarkable precision now. Infrared telescopes, both ground-based and space-based, map Jupiter's thermal emissions. They've found that Jupiter's poles are slightly warmer than expected, possibly because of auroral heating. They've found that some regions of Jupiter's atmosphere are hotter than others, suggesting localized upwellings of warm gas. They've found that Jupiter's heat output varies slightly over time, though the variations are small and not yet fully understood. And there's another consequence of Jupiter's internal heat. It affects the planet's evolution. Planets cool over time. They radiate energy into space. Eventually, they reach thermal equilibrium, where they only emit as much energy as they receive from their star. Earth reached that equilibrium long ago. Mars too. But Jupiter hasn't. Not yet. Jupiter is still in the process of cooling, still releasing the heat of its formation, mixed with the ongoing heat of helium rain and gravitational contraction. Scientists estimate Jupiter will continue radiating excess heat for tens of billions of years, longer than the Sun will last, longer than the solar system's current configuration will remain stable. Jupiter is a slow engine burning its own structure, as fuel glowing faintly in a spectrum we can detect but not see with unaided eyes. And maybe there's something profound in that, in the idea that a planet can be its own furnace. That gravity alone, the simplest force, the one we experience every moment of our lives, can generate enough energy to keep a world warm for eons. No chemistry required, no nuclear reactions. Just mass pulling inward, resisting itself, creating heat from the tension between falling and holding. If you could somehow feel Jupiter's warmth, if you floated in space just above its clouds, you wouldn't notice anything. The heat radiates into a vacuum that can't conduct it. The sun would feel warmer even from Jupiter's distance, but instruments would detect it. Sensitive thermometers would register the faint infrared glow. And if you waited long enough, measured carefully enough, you'd see that Jupiter is not a dead cold world, but a living, breathing engine of slow transformation. There's a lesson maybe in Jupiter's patience, in the fact that something can glow for billions of years without burning out. That warmth doesn't require fire, that even in the coldest reaches of space, even 500 million miles from the sun, energy finds a way to persist. And now, with Jupiter's inner warmth still glowing in our thoughts, it's time to turn our attention outward again. Because Jupiter isn't alone. It's never been alone. Circling it locked in, orbits both ancient and strange, is an empire of moons, 95 worlds each with its own story. And 4 of them, the largest, hold secrets that might change everything we think we know about life in the universe. Those 4 secrets have names: Io, Europa, Ganymede, and Callisto. The Galilean moons discovered on that cold January night in 1610, when Galileo first pointed his telescope skyward. He saw them as tiny points of light moving in a line beside Jupiter, and realized the universe was larger than anyone had dared imagine. 4 centuries later, we know those points of light are worlds, strange worlds, violent worlds, worlds that challenge everything we thought we knew about where life can exist. But Jupiter doesn't have just 4 moons. It has 95. 95 worlds caught in its gravity, ranging from giants larger than Mercury to tiny rocks barely a kilometer across. Some orbit close, completing their journeys in hours. Others drift far out, taking years to circle once. Some rotate with Jupiter locked in tidy orbits. Others spin backward, rebellious, moving against the flow like salmon swimming upstream. Let's begin with Io, the closest of the Galilean moons, the most volcanic object in the entire solar system. If hell had a landscape, it might look like Io. Io is approximately the same size as Earth's moon, 3,600 kilometers across. But where our moon is dead cold and silent, Io is alive with fire. More than 400 volcanoes cover its surface. 400. Some erupt, continuously spewing sulfur and sulfur dioxide hundreds of kilometers into space. Others lie dormant for years before suddenly exploding with plumes that dwarf anything Earth has ever produced. When Voyager 1 flew past Io in March of 1979, mission scientists expected to see a quiet, cratered world, something like Earth's moon, something ancient and still. Instead, they saw plumes, enormous fountains of material rising 300 kilometers above Io's surface. At first, they thought the images were corrupted. Then they realized what they were seeing: active volcanism, happening in real time, right there while they watched. It was the first time humans had ever witnessed volcanic activity on another world. The first confirmation that geology wasn't unique to Earth, that other planets, other moons could be just as restless, just as dynamic as our own. And Io was more active than anyone could have predicted. Not one volcano, not 10, hundreds. The largest volcano on Io is called Loki Patera. It's not a mountain like volcanoes on Earth. It's a lava lake, a vast depression filled with molten rock roughly 200 kilometers across. That's larger than the state of Connecticut. And it's constantly active. The lava circulates, cooling at the edges, sinking fresh magma, rising to replace it. Scientists estimate Loki Patera produces more heat than all of Earth's volcanoes combined, a single volcanic feature outshining an entire planet's geological activity. But why is Io so volcanic? The answer is tidal heating. Io orbits Jupiter in just 42 hours, close enough that Jupiter's gravity pulls on Io with tremendous force. But Io doesn't orbit alone. Europa and Ganymede, the next 2 moons outward, pull on Io as well. Their combined gravitational tugs force Io into a slightly elliptical orbit. And as Io's distance from Jupiter changes, Jupiter's gravitational pull changes. Stronger when Io is close, weaker when Io is far. This changing pull flexes Io, squeezes it, stretches it, like kneading dough. And that flexing generates heat through friction. Io's interior, unable to remain rigid, melts. The rock becomes molten. And that molten rock finds its way to the surface, erupting as lava, ash, and gas. Scientists estimate Io's surface is completely resurfaced every million years or so. Every crater, every feature buried under new volcanic flows. It's the youngest surface in the solar system, a world in constant transformation, never still, never quiet, always burning. And the colors. Io is painted in shades of yellow, orange, red, and white. Sulfur deposits, sulfur dioxide, frost, and volcanic rock create a palette unlike anywhere else. From a distance, Io looks almost like a pizza, mottled, chaotic, beautiful in a way that's both alien and strangely familiar. But Io is also dying in a sense. The volcanic activity that makes it so dynamic is also stripping it away. Every eruption sends material into space. Some of it falls back. Some escapes, feeding the Io plasma torus we discussed earlier. Over billions of years, Io has lost a significant portion of its mass. and it will continue losing mass until eventually the tidal forces weaken, or Io's orbit stabilizes, but that won't happen for a very long time. Now let's drift outward to Europa, the ice moon, the ocean world, the most likely place in the solar system aside from Earth where life might exist right now. Europa is slightly smaller than Io, 3,100 kilometers in diameter. But where Io is, Fire Europa is ice. Its surface is frozen solid, covered in water ice that's been polished smooth by some process scientists don't fully understand. There are almost no craters on Europa, almost no mountains, just cracks. Vast branching cracks that crisscross the surface like veins or rivers frozen mid-flow. But beneath that ice, scientists believe is an ocean, a global ocean. Liquid water perhaps 100 kilometers deep, covering the entire moon. More water in total volume than all of Earth's oceans combined. And that water has been liquid for billions of years, kept warm by the same tidal heating that powers Io's volcanoes, though Europa experiences far less heating due to its greater distance from Jupiter. How do we know there's an ocean? We've never drilled through the ice, we've never sampled the water, but we have evidence. Magnetic field measurements from the Galileo spacecraft suggest Europa has a conductive layer beneath its surface, something that can carry electrical currents. Salt water would fit. So would a metallic core, but other data makes that less likely. The way Europa's ice flexes and shifts suggests something fluid below, and computer models of Europa's interior, based on its mass and density, consistently predict a subsurface ocean. But an ocean alone doesn't mean life. Life needs energy, it needs chemistry, it needs time, and Europa might have all three. The ocean floor, if it exists, could have hydrothermal vents, cracks in the rocky mantle below the water where heated minerals dissolve into the ocean, providing nutrients. On Earth, hydrothermal vents support entire ecosystems. Strange alien-looking creatures that don't need sunlight, that live off chemistry alone. Could the same thing happen on Europa? We don't know, but the possibility is tantalizing enough that NASA has planned a mission. Europa Clipper, launched in October of 2024, will arrive at Jupiter in the 2030s. It won't land on Europa. It won't drill through the ice. But it will fly past Europa dozens of times, using instruments to study the moon's ice shell, measure the thickness, look for plumes of water vapor erupting from cracks. If those plumes exist, Clipper might be able to sample them, analyze their chemistry, and determine whether Europa's ocean contains the ingredients for life. And there's another clue. Europa's surface shows evidence of recent geological activity. Some of the cracks are dark, filled with material that seems to have welled up from below. Scientists call these features chaos terrain, regions where the ice has broken apart, jumbled, refrozen in new configurations. It's as if something from below pushed upward, fractured the surface, and left behind a scar. If Europa's ocean is in contact with the surface even occasionally, that changes everything. It means material from the ocean can reach the surface where we can study it. And it means material from the surface, including organic molecules delivered by meteorites, can sink into the ocean. Exchange, mixing, chemistry. But here's the challenge. Europa's ice shell might be 20 kilometers thick, maybe more. Drilling through 20 kilometers of ice on Earth is difficult. Doing it on a moon 400 million miles away in Jupiter's intense radiation with no human assistance is nearly impossible, at least with current technology. But scientists are working on it, designing robots that could melt their way through ice, submarines that could explore the ocean below, concepts for missions that won't happen for decades but are already being imagined. Next is Ganymede, the largest moon in the solar system. Larger than Mercury, larger than Pluto. So large that if it orbited the Sun instead of Jupiter, we'd call it a planet. Ganymede is 5,200 kilometers across. Massive, heavy. And unlike any other moon, Ganymede has its own magnetic field. Not as strong as Earth's, but strong enough to create a small magnetosphere. a protective bubble within Jupiter's much larger magnetosphere. Scientists believe this magnetic field is generated by a liquid iron core deep inside Ganymede, a core that's still partially molten, still convecting, still creating the dynamo effect that produces magnetism. Ganymede's surface is divided into two types of terrain: dark regions, ancient and heavily cratered dating back billions of years, and bright regions younger and grooved, covered in parallel ridges and valleys that stretch for hundreds of kilometers. Scientists think the bright terrain formed when Ganymede's icy crust fractured and shifted, perhaps due to tectonic activity driven by tidal heating or internal convection. And like Europa, Ganymede might have an ocean, a subsurface ocean buried even deeper beneath thicker ice. Observations from the Hubble Space Telescope detected auroras on Ganymede, faint glows near its poles, and the way those auroras shift suggests the presence of a conductive layer below the surface. Salt water again. An ocean trapped between layers of ice, possibly in contact with a rocky mantle below. But Ganymede's ocean, if it exists, is likely much colder and less accessible than Europa's. And the thick ice above it makes the possibility of life more remote. Still, it's there. Another hidden sea in the outer solar system. Another place where water, that essential ingredient, exists in quantities we can barely comprehend. Finally, Callisto, the outermost of the 4 Galilean moons, the most heavily cratered object in the solar system, a world that looks ancient because it is ancient. Callisto orbits far enough from Jupiter that tidal heating is minimal. Its surface hasn't been resurfaced like Io's. It hasn't fractured like Europa's or Ganymede's. It's just old, cratered, quiet. Every impact that struck Callisto in the past 4 billion years is still visible, a geological record stretching back to the solar system's violent youth. The largest impact basin on Callisto is called Valhalla. It's enormous, 1,600 kilometers across, surrounded by concentric rings that ripple outward like frozen waves. The impact that created Valhalla was so powerful it nearly shattered Callisto. Scientists think the moon's icy crust absorbed the shock, preventing total disintegration. But the scar remains, visible, permanent. And yet, Callisto might also have a subsurface ocean. Magnetic field data from Galileo suggests it. Though Callisto's ocean, if real, would be deeper and colder than Europa's or Ganymede's, less likely to support life, less interesting perhaps to those searching for biology, but still remarkable. Still a reminder that water is everywhere in the outer solar system, hidden, buried, waiting. Beyond the Galilean moons, Jupiter's other 91 moons are smaller, stranger, more chaotic. Many are irregular moons, captured asteroids pulled into Jupiter's orbit by gravity. They're lumpy, dark, and orbit in all directions. Some are only a few kilometers across, barely visible even through powerful telescopes. Others are larger, dozens of kilometers wide, but still insignificant compared to the giants. These irregular moons tell a story of capture and chaos, of a solar system still evolving, still rearranging itself. And they remind us that Jupiter's influence extends far beyond its visible disk, far beyond its magnetosphere. Jupiter shapes orbits, captures objects, holds them for millions of years before sometimes losing them again to some other gravitational dance. And every one of these moons, from the largest to the smallest, is caught in Jupiter's grip, held, shaped, warmed or frozen depending on their distance. They are Jupiter's empire, Jupiter's children, and they will circle the giant as long as Jupiter exists, loyal not by choice, but by the simple, inexorable mathematics of gravity. But Jupiter itself is more than just a planet with moons. It's something else. Something that almost became something greater. And understanding what Jupiter is requires understanding what it isn't, and what it might have been if the universe had been just slightly different. That difference is mass, just mass, nothing more. Jupiter needed to be 75 times heavier to become a star, 75 times more hydrogen packed into the same space, 75 times more gravity pulling inward. And then, at the core, pressure would have been enough. Temperature would have been enough. Hydrogen atoms would have been crushed together, hard enough to fuse, releasing energy light heat. Jupiter would have ignited, but it didn't. Jupiter gathered as much material as it could from the early solar nebula, but there simply wasn't enough left. The Sun had already claimed most of the hydrogen. Jupiter got the leftovers. Enough to become the largest planet in our system, not enough to become the smallest star. And yet, Jupiter is remarkably similar to a star in composition. 90% hydrogen, 10% helium. Trace amounts of heavier elements like methane, ammonia, water vapor. The same mixture that fills the Sun. The same mixture that filled the cloud from which both were born. If you could somehow scoop up a piece of Jupiter and analyze it chemically, you'd find it resembles the Sun more than it resembles Earth. Jupiter is a star that never quite made it. A star frozen in adolescence forever, waiting for a transformation that will never come. Scientists sometimes call objects like Jupiter sub-brown dwarfs. Brown dwarfs are objects heavier than planets, but lighter than stars. They glow faintly from their own heat, but they never achieve true hydrogen fusion. The smallest brown dwarfs are about 13 times Jupiter's mass. That's the threshold where deuterium fusion begins. Deuterium, a heavier form of hydrogen with an extra neutron, fuses at lower temperatures and pressures than normal hydrogen. Brown dwarfs can fuse deuterium for a while, glowing dimly before exhausting their supply and fading. But Jupiter is below even that threshold. It never fused anything. It simply formed contracted, heated up from compression, and has been slowly cooling ever since. A failed star, a failed brown dwarf, just a planet. The largest planet, yes, but still just a planet. Still, there's something poignant in Jupiter's near miss. If the solar nebula had been just slightly richer in hydrogen, if Jupiter had formed slightly earlier and claimed more material before the Sun swept it away, if a few more asteroids had crashed into young Jupiter and added their mass to its total, we might be living in a binary star system. The Sun and Jupiter both burning. Two lights in the sky instead of one. What would that have been like? For one, there would be no night. Not true darkness anyway. When the sun set, Jupiter would rise glowing red and dim, casting faint shadows. The sky would never be fully black. Stars would be harder to see. Ancient astronomers would have had a much more difficult time mapping the heavens. And Earth's climate would be different. Not dramatically. Jupiter, even as a red dwarf star, would be far away and far dimmer than the sun. But it would add heat. A little. Enough to shift weather patterns, perhaps. Enough to make winters slightly warmer and summers slightly stranger. But more importantly, the orbits would be different. Binary star systems are complex. Planets in such systems either orbit close to one star or far from both. There's no stable middle ground. Earth orbiting the Sun at its current distance might not have been stable if Jupiter had become a star. We might have been flung into a wider orbit, or ejected entirely sent drifting through interstellar space, or pulled inward eventually consumed by the Sun. Life, as we know it, might never have evolved, all because Jupiter was almost but not quite heavy enough. In other solar systems, we've found planets like Jupiter, thousands of them. Gas giants orbiting distant stars. Some are larger than Jupiter, some smaller, and a surprising number orbit much closer to their stars than Jupiter orbits ours. These are called hot Jupiters, massive planets scorched by their proximity to their suns, completing orbits in days instead of years. The first exoplanet ever discovered around a sun-like star was a hot Jupiter. In 1995, astronomers Michael Mayor and Didier Queloz detected a planet orbiting the star 51 Pegasi. They named it 51 Pegasi b. It was roughly half the mass of Jupiter, but it orbited its star in just 4 days. 4 days. So close that its surface temperature was estimated at over 1,000 degrees Celsius. At first, astronomers thought it was a mistake. Gas giants weren't supposed to orbit that close to their stars. According to models of planetary formation, giant planets should form far from their stars, where it's cold enough for hydrogen and helium to condense. Closer and only rocky planets should exist. But 51 Pegasi b was real, confirmed by multiple observations, and soon more hot Jupiters were found. Dozens, hundreds. Scientists now believe hot Jupiters formed farther out like Jupiter, but then migrated inward. Gravitational interactions with the protoplanetary disk or with other planets pushed them toward their stars. Some were probably consumed by their stars. Others stabilized in close orbits and remain there, slowly losing mass as stellar wind strips away their atmospheres. And this raises a question. Could Jupiter have migrated? Could it have moved inward billions of years ago, disrupting the inner solar system before settling into its current orbit? The answer, according to some models, is yes. It's called the Grand Tack hypothesis. The idea is that young Jupiter forming in the outer solar system began spiraling inward due to interactions with the gas disk. It moved sunward, perhaps as close as Mars's current orbit. As it moved, it scattered asteroids, disrupted forming planets, and generally wreaked havoc in the inner solar system. But then Saturn formed, and Saturn's gravity interacted with Jupiter's. The two giants locked into a resonance, and instead of continuing inward, they both reversed course. They tacked like a sailboat turning against the wind and migrated back outward to roughly their current positions. If this hypothesis is correct, Jupiter's migration might explain several puzzles. Why Mars is so small? Why the asteroid belt exists? Why Earth survived at all? Jupiter could have easily destroyed Earth's orbit during its inward migration. Instead, it turned back, leaving the inner solar system just disturbed enough to be interesting, but stable enough to support life. But we're not certain. The Grand Tack is one model among many. Other models suggest Jupiter stayed where it formed, never migrating significantly. The truth remains hidden in the gravitational scars and orbital resonances that still echo through the solar system today. What we do know is that Jupiter's presence shaped everything. Even if it didn't migrate, even if it stayed put, its gravity influenced the distribution of material in the early solar system. It prevented a planet from forming in the asteroid belt. It flung comets inward, delivering water to Earth. It captured asteroids into Trojan swarms that orbit ahead of and behind it, locked in stable gravitational balance. And Jupiter continues to shape things now. Every comet that passes too close gets deflected. Every asteroid that wanders inward feels Jupiter's pull. Even spacecraft, tiny and fragile, use Jupiter's gravity to accelerate, to change course, to reach destinations they couldn't otherwise achieve. Voyager 1 and Voyager 2 both flew past Jupiter, stealing a tiny fraction of its orbital momentum, gaining speed, and hurtling toward the outer planets and beyond. Jupiter doesn't notice. It's far too massive to be affected by spacecraft. But the principle is the same. Gravity is influence. Gravity is change. And Jupiter's gravity is stronger than any other planet's, stronger than all the other planets combined. If you could somehow remove Jupiter from the solar system, everything would change. Asteroid impacts on Earth would increase dramatically. Comets would fly through the inner solar system unchecked. The orbits of the other planets would shift slowly over millions of years, destabilizing in ways we can't fully predict. Mars might drift outward. Earth's orbit might become more elliptical. The delicate balance that makes our solar system stable would unravel. We owe Jupiter more than we realize, not just for past protection, but for ongoing stability. Jupiter is an anchor, a gravitational lighthouse, a presence so massive it keeps everything else in line. And maybe that's Jupiter's true purpose, if we can call it purpose. Not to become a star, not to rival the sun, but to be what it is, a guardian, a stabilizer, a giant that exists not for itself, but for the smaller, quieter worlds that orbit nearby. There's a strange kind of beauty in that, in something so massive, so powerful, playing a supporting role. Never the center of attention, but always essential. Always there. And as Jupiter continues its slow orbit as it has for billions of years and will for billions more, we're left with questions. Questions about what Jupiter has been, what it is now, and what it will become as the solar system ages, as the sun swells and dims, as everything we know transforms into something we can't yet imagine. Those transformations are already beginning, slowly, imperceptibly, but inevitably. Jupiter is changing. The Great Red Spot is shrinking. The magnetosphere fluctuates. The moons evolve. And far in the future, billions of years from now, Jupiter will witness the death of everything it has ever known. But let's not rush to the ending just yet. Let's consider what comes next. What happens to Jupiter in the near future, in our future, in the lifetimes of missions already planned and civilizations not yet born? The Great Red Spot, that ancient storm we talked about earlier, continues to contract. Scientists have been measuring it carefully for over a century. In 1830, it was roughly 40,000 kilometers wide. By 1900, 35,000. By 2000, 20,000. Now in the 2020s, it measures approximately 16,000 kilometers across. Still enormous, still larger than Earth, but undeniably shrinking. At its current rate of contraction, some scientists estimate the Great Red Spot might disappear entirely within the next 20 to 40 years. Others think it will stabilize at a smaller size and persist for centuries more. No one knows for certain. We're watching something that has existed longer than human civilization slowly fade, and we don't know if we'll see the end or just a transformation. Imagine being the generation that witnesses the last rotation of the Great Red Spot, the final swirl, the moment when centuries of continuous motion finally still. It would be like watching a star go out, like seeing an ancient tree fall, a reminder that even the most enduring things eventually change, but Jupiter will remain. With or without the Great Red Spot, Jupiter will continue to spin, to glow, to hold its moons in their orbits. New storms will form. Other features will emerge. Jupiter has had storms before the Great Red Spot and will have storms after. The planet itself is far more permanent than any individual feature on its surface. In the more distant future, perhaps 50 million years from now, Jupiter's orbit will shift slightly. Not because of anything Jupiter does, but because of the gravitational influences of the other planets. Saturn, Uranus, Neptune. All of them tugging, nudging, creating tiny perturbations that add up over geological time. Jupiter might drift a few million kilometers closer to the Sun, or farther away. The change will be small, but it will affect the moons. Io's volcanism might intensify or weaken. Europa's ice shell might thicken or thin. Ganymede and Callisto might experience subtle shifts in their orbits. And in 5 billion years, something much more dramatic will happen. The sun will begin to die, not explode, not vanish, but transform. It will exhaust the hydrogen in its core, and fusion will move outward into a shell surrounding the core. The sun will swell, becoming a red giant, expanding until it consumes Mercury, then Venus, possibly Earth. Jupiter at 5 astronomical units away will be safe. The sun won't reach that far, but Jupiter will feel the change. The sun's luminosity will increase dramatically, 100 times brighter, maybe more. Jupiter's atmosphere will warm. The ice on its moons will begin to melt. Europa's subsurface ocean might reach the surface. Ganymede's ice could crack and flow. For a brief period, geologically speaking, Jupiter's moons might become warm enough for liquid water to exist on their surfaces. Could life emerge then? Could organisms from Europa's ocean, if they exist, finally see sunlight? Could something frozen and dormant on Callisto wake up and flourish in the sudden warmth? It's possible. Unlikely, but possible. The red giant phase won't last forever. Maybe a billion years. Maybe less. But that's a long time for evolution, long enough for something to happen, long enough for a second chance at life in the outer solar system. Eventually, the sun will shed its outer layers. They'll drift away as a planetary nebula, glowing and beautiful, until they fade into the interstellar medium. What's left will be a white dwarf, a dense, hot core no larger than Earth, but containing most of the sun's original mass. It will shine dimly, cooling over trillions of years until it becomes a black dwarf, a cold, dark cinder in space. And Jupiter will remain, orbiting the white dwarf, still massive, still holding its moons, but cold now, truly cold. No more internal heat, no more storms. The atmosphere will freeze layer by layer until Jupiter becomes a solid ball of hydrogen ice, a fossil of what it once was. But even then, Jupiter won't disappear. It will orbit the dead sun for trillions of years, longer than the current age of the universe, longer than stars will continue to form in galaxies. Jupiter will outlast almost everything, a monument to persistence, a reminder that some things once created endure far longer than the forces that made them. But let's come back to now, to the present, to the missions we're planning and the questions we're still asking. Because understanding Jupiter isn't just about the past or the distant future, it's about what we do next. NASA's Juno mission, which arrived at Jupiter in 2016, has revolutionized our understanding of the planet. It's still there, still orbiting, still sending back data. Juno has mapped Jupiter's gravitational field with unprecedented precision. It's measured the depth of the Great Red Spot. It's discovered that Jupiter's magnetic field is far more complex than anyone expected, with patches of reverse polarity near the equator. It's captured stunning images of Jupiter's poles, revealing cyclones arranged in geometric patterns that no one predicted. But Juno won't last forever. Its orbit takes it through intense radiation belts. Every pass damages its electronics a little more. Eventually, it will fail. And when it does, NASA plans to crash it into Jupiter, ensuring it doesn't accidentally contaminate Europa or any other moon that might harbor life. Juno will become part of Jupiter, its atoms scattered through the atmosphere it spent years studying. A fitting end, perhaps. Beyond Juno, there's the European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in April of 2023. JUICE is currently on its way to Jupiter, scheduled to arrive in 2031. Its primary targets are Ganymede, Europa, and Callisto. It will orbit Ganymede, the first spacecraft ever to orbit a moon other than Earth's. It will study the subsurface oceans, map the surfaces, measure the magnetic fields, search for signs of habitability. And then there's Europa Clipper, NASA's mission to Europa, launched in October 2024. It will perform dozens of close flybys of Europa, studying the ice shell, measuring its thickness, searching for plumes of water vapor that might be erupting from cracks. If those plumes exist, Clipper might fly through them, sampling the water, directly analyzing its chemistry without ever landing. These missions represent humanity's best effort to understand Jupiter and its moons. They're expensive, difficult, risky, but they're necessary. Because Jupiter holds answers about how planets form, how solar systems evolve, and most importantly, where life might exist beyond Earth. If Europa's ocean contains life, even microbial life, it changes everything. It means life isn't unique to Earth. It means life can arise wherever the right conditions exist. Water, energy, chemistry time. If Europa has life, then so might Enceladus, Saturn's icy moon. So might Titan with its methane lakes. So might 1,000 other moons and planets scattered through the galaxy. And that would be the most profound discovery in human history, more significant than fire, agriculture, electricity, or space flight. Because it would mean we're not alone. Not in the way we usually think of that phrase, with alien civilizations sending radio signals, but alone in a simpler, more fundamental sense. Life on Earth would no longer be the only life. We'd be part of a larger community, a cosmic ecosystem that spans worlds and moons and the dark spaces between. But even if we find nothing, even if Europa's ocean is sterile, Ganymede's ice is lifeless, and Jupiter's moons hold no surprises, the search itself is valuable because it teaches us about our own planet, about how fragile and precious life is, about how unlikely and extraordinary our existence might be. Jupiter has taught us that planets are more than rocks and gas. They're systems, ecosystems in a sense. They interact with their moons, their stars, their neighbors. They shape and are shaped by everything around them, and they endure. Not forever, nothing lasts forever, but for time scales so vast, they might as well be eternal. And what about us? What role do we play in Jupiter's story? Right now we're observers, visitors. We send machines to look and listen, but we don't touch. We don't change anything. Jupiter doesn't know we exist, doesn't care that we've named its storms or counted its moons. We're as insignificant to Jupiter as a single bacterium is to us. But maybe that will change. Maybe someday humans will visit Jupiter, not land on it. That's impossible, but orbit it, build stations near its moons, mine ice from Europa or Callisto, use Jupiter's gravity to launch missions deeper into space. Maybe Jupiter, the guardian of the inner solar system, will become a gateway to the outer solar system, a waypoint on journeys to the Kuiper Belt, the Oort cloud, and eventually the stars. That future is far away, generations at least, maybe centuries, but it's not impossible. And if it happens, Jupiter will still be there, patient, massive, unchanged in any way that matters, waiting for us to arrive, waiting to be seen not through telescopes or by robots, but by human eyes. Until then, Jupiter remains what it has always been: a giant, a guardian, a mystery, a world so large it defies comprehension, so strange, it challenges imagination, so beautiful, it inspires wonder. Every time you see it in the night sky, that bright, steady light that doesn't flicker, remember what you're looking at. Not just a planet, but a story, a history, a future. Jupiter has been watching Earth for 4.5 billion years. It's seen everything: the formation of oceans, the emergence of life, the age of dinosaurs, the rise of mammals, the birth of humanity. And it will continue watching long after we're gone, long after everything we've built has crumbled, long after Earth itself is swallowed by the dying sun. And maybe that's the most comforting thought of all, that no matter what happens to us, no matter how brief our moment in cosmic time, we existed in a universe that also contained Jupiter. We looked up at the same sky our ancestors looked at and saw the same light. We sent machines across unimaginable distances to touch briefly something vast and ancient and indifferent. And in that touching and that reaching, we became part of Jupiter's story. A small part, a footnote maybe, but a part nonetheless. So rest now. Let Jupiter's light fade into your thoughts like a distant memory. Let the storms and moons and magnetic fields drift into dreams. You've traveled far tonight, across millions of kilometers, through clouds and radiation, past volcanoes and oceans and ice. You've seen wonders that most people will never imagine. And you've done it all without leaving your bed. Sleep well knowing that Jupiter is still out there, still spinning, still glowing, still holding its empire of moons, and guarding the inner solar system from dangers we'll never see. The giant is patient, the giant is eternal, and the giant in its own way keeps us safe. Thank you for drifting with us through this quiet exploration of Jupiter. We hope these stories brought you both knowledge and peace. If you'd like more journeys like this, more cosmic tales told softly, we'll be here waiting to wander with you again through the infinite beautiful dark. Until then, rest gently, dream of distant worlds, and good night.